We wrapped up all the waveforms last time about on the half-wave rectifiers chapter. So today we'll skim through the slides, make sure everything was covered, as well as look at some of the equations. The first, and again, you have an opportunity to ask questions again about the waveforms and the circuits if you have questions remaining. Yeah. So the first was the half-wave rectifier with a resistive load. We went through that, and again, the objective of these rectifiers is to create DC from the AC input, right? So definitely there's an interest to calculate the average value, which is the DC value that we want to calculate as the output. We would like to know what DC value I can put across my load. So then DC value is the average value, which is 1 over the period. In this case, the period is the full cycle, right? So it's a full cycle. I have voltage on the output during half of that, and then it's 0 the rest of the cycle. So 1 over the period, integration over the full period of what? Of my waveform. My waveform just happens to be the V maximum sine omega t. It's the same equation as the input voltage equation, from 0 to pi, and then from pi to 2 pi it's 0. So if you perform the integration, you'll get V maximum over 2. So that's the average value of voltage. Can we change that? Okay, is this something that's controllable? It's not controllable. It's always fixed depending on your maximum input voltage value, and that's it. So you can change your input voltage, but then what are you doing? All right, it's the input voltage is typically fixed to the power supply. For example, in an application like this, or an AC application generally, where you have a power system connected to the AC grid. That AC grid is supplying a fixed AC voltage, right? So in this application, you cannot change the DC voltage, which may be okay for certain applications, may not be okay for others, right? So you may select your load to suit something like this. Or what's the solution that we proposed later on in the chapter? How did we propose to control the output voltage in an AC to DC converter in this chapter? Gated what? Gated diode. What is it called? Yeah, exactly. So we use an SCR instead of a diode. We proposed we said we can use a SCR instead of a diode in this case, and that way we can control the input voltage and output voltage, right? So then we moved on to the RL load. So this is where we first start seeing equations. Yeah. Because in this case, what is the equation for the average output current? What's the average output current in this case? Remember, guys, only components at the same frequencies will produce the average power, right? So average power means I have average voltage and I have average current. So my average voltage, I calculated my average voltage is V maximum over pi. And this is a resistive load. So what's the average current? Divided by the resistance. Divided by the resistance value. That's it. Right? So that's the average value of current in this case, which means the average value of power is the multiplication of both of these together. Right? And then we moved on to this circuit. In this case, the average value of current is not merely the same as or as simple as, or finding the equation for current, for example, is not simple like the previous case. Previous case, it was just a pure sine wave. I know the equation of a sine wave. In this case, we have a different phenomena because of the availability of the inductance as well. It's an element that can store energy. So if you remember what we did in 214, or before that, first what we would do typically is do KVL around the circuit, right? So V maximum sine omega t, right? This voltage here is equal to the output voltage. The output voltage is equal to the summation of the resistance voltage and the inductance voltage. So V maximum sine omega t is equal to Ri of t plus L di by dt, which is the voltage across the inductor, right? So this is the first order differential equation that describes this circuit. We would like to calculate, this is the full equation. So we would like to calculate, our objective is to calculate the current. Because if I calculate the current, then I can calculate the voltage across the resistor, voltage across the inductor, power losses, efficiency. I can do lots of stuff if I could do that, right? So then, how do you calculate the current? You have an RL circuit where the inductance has a possibility to store energy, right? There's certain states where it can store energy, right? So we have to account for that. So it's like having a circuit with two sources, right? So you would perform superposition, right? So assume the inductance has no initial current. If the inductance has no initial current, how would you find the current in the circuit where you have an AC source across a resistor and an inductance? Inductance initially has zero current. Hmm? No, no. AC current. This is not DC current. This is AC current. VL is equal LdI by dt. As long as there is a di by dt, so there is a variation of current with time, that means the inductance exists. There is a voltage drop across it, right? So for AC circuits, inductances exist. They exist in the circuit. So how do you calculate the current flowing through a circuit? This is an AC source across an impedance. How do you calculate the current? Assuming there's exactly, it's the voltage over the impedance. So it's the voltage. It's the voltage. So the voltage over the impedance. So that's the forced response. The forced response is due to the fact that I have a source. Natural response of the circuit is the response due to the fact that I have initial current flowing in my inductor, right? So the equation for I of t, we split it into two portions. The forced response and natural response. That's the superposition that we're using, right? We're using one time this source and one time the initial current in the circuit, and we're looking at the sum of these will be the full current that's flowing in the circuit, right? So what does the forced response equal? The forced response equals the voltage source that you have in the circuit divided by the impedance, right? So it's V maximum sine omega t, right? That was my voltage source, V maximum sine omega t. And then where did this theta come from? We divided the voltage by the magnitude of the impedance. Z here is only a magnitude. I'm sorry they didn't put these absolute values around it to indicate that it's a magnitude, but they show that here. So Z here is only the magnitude of the impedance. So if I'm dividing by, go away. I want this to go away. So if I divide by the magnitude of the impedance, yeah. So if I divide by the magnitude of the impedance, then the impedance is a complex number, right? It has a magnitude and an angle. So I can keep the angle on the bottom, in the denominator, or I can bring it to the top, right, and subtract it from the angle of the voltage, because I know that the voltage has an initial angle of 0. So if you have it has a magnitude of V maximum, an angle of 0. So it's like in the numerator I have V maximum angle 0, in the denominator I have Z angle theta. So I bring theta to the top, and it's V maximum sine omega t minus theta, right? So I just add this theta to the top. So everybody's okay with this? It's the phasor representation of the voltage. So if you have V max sine omega t, this is a quantity that is changing with time at a frequency 2 pi f, right? So it's a sinusoidal quantity that is changing with time at a frequency of omega or f, which is part of the 2 pi f, right? So I can take any sinusoidal quantity and write it in phasor form. When you take a sinusoidal quantity and you represent it in phasor form, you take its magnitude. You can represent it in this real and imaginary plane as a magnitude and an angle, right? So this will have a magnitude of V maximum, and at an angle of, in this case, it starts at 0. So this angle should be 0. So this angle, theta V here, should be 0, right? So I should draw it like this. So this would be the phasor representation of V maximum sine omega t, right? How about impedance? Z is also a complex quantity. It's also represented using a magnitude Z and an angle theta, because I have certain amount of resistance. This is my real component, the imaginary component of my impedance. I have some amount of resistance and then some amount of inductance, for example, right? So this will be Z in phasor form as a magnitude, and it will have an angle of theta. In this case, that's what they call it, right? So if I have V maximum angle 0 over Z angle theta, then that's exactly the same as V maximum over Z angle minus theta, right? So if I would like to take this phasor and represent it in the time domain, how would I do that? I would write it as V maximum over Z. These are magnitudes, and it's sine omega t minus theta in the time domain. Okay? So that's time domain versus instantaneous value versus phasor domain. Okay, so it's nice. You need to switch between domains sometimes. So I divided the voltage at my input by my impedance, and I brought the angle up here. The impedance angle, I brought it up here. And they just rewrote the definition of Z there. The magnitude of Z is the resistance squared by omega L squared, and theta is the angle of the impedance, which is inverse tan omega L over R. Everybody's comfortable with that? And so that takes care of the forced response. How about the natural response? Natural response. I put this source is now a short circuit. And I just have, the diode of course is a short circuit because I have current flowing in the circuit. So I simply have an RL circuit with initial current flowing through the inductor. So I basically remove this component here of my differential equation and put a 0 here, right? What is the solution to Ri of t plus L di by dt equals 0? I can bring Ri of t on one side and solve it. Or I know that the solution of a first order differential equation, and this is we will only use first order differential equations in the course, right? So the solution to a first order differential equation will always be a e to the exponential form, right? And then we can find the value of a from the conditions of the circuit. So for example, initially I know that the current is 0, for example. If the current is 0, then after I take this now, natural response, and I plug it into my equation for current. So I add the forced component and the natural component. So I have a big equation for current that has a, an unknown value. So what do I do next? I look at the waveforms. From the waveforms, I know what? That initial value of current is 0. I also know that at beta, the value of current is also 0. So I knew two things about the current. But beta is a value that I don't know about now, right? I don't know. It will depend on the value of the R and the L where this beta occurs, right? The inception and the extinction angle is depending on the value of R and L. But I know this very well. It happens at 0. So now I wrote my equation for current, which is the forced response plus the natural response. It includes an A value. So this A, I know that the initial value of current is 0. So I of 0 is equal to 0. I solve the equation for A, and then I take this value of A and plug it back into my time domain equation, right? So I of t is equal to this value, right? I can write it in terms of time, or I can write it in terms of angular angular frequency, right? So I can, instead of t, I can put omega t here, and then in this case I also have to change this time and this time constant to the same sort of angular frequency terms, right? So I would have to multiply the t by omega and the tau by omega, right? So I can have the same units. Okay, so either I of t or I of omega t. Everybody's okay with this? Again, you don't have to memorize it. It's in the equation sheet, and it's always going to be the same solution. The a e to the minus t over tau will always be the solution to the first order differential equation, and we will only have first order differential equations, right? So the most difficult thing that we will do is a shift of axis. So instead of a e to the minus t over tau, a e to the minus t, minus, keep the minus outside and then add a shift in angle. That's the most complicated thing that we will do from a differential equation perspective. But it's good review. It's easy for you. It's to review sort of what happens in differential equations. It's just a quick review of differential equations. So now I found out what I have an equation for current, right? I would like to be able to find beta, right? Remember last time we said we want to be able to find beta, and it will depend on the value of R and L. Sure, it will depend on the value of R and L and the equation of current, right? So I have my equation of current, right? I know what happens at beta. At beta, the current becomes zero as well, right? Current becomes zero at beta as well. So if current becomes zero at beta, I should be able to solve for beta by equating my equation for current at zero. So I beta is equal to zero. Instead of omega t, I put the beta and equate that to zero. It just happens to be that this equation is a nonlinear equation. So you cannot solve it, you cannot find a value in closed form solution to it manually. So not like the A value, right? Because here it's inside the sign, inside the exponent, so it's an equation you will have to solve numerically. So your calculators do that. I mean, I'm pretty sure your calculators do that. That's what we've been doing all the time. The students were able to use their calculators to solve for beta. And you can do that in the exam, no problem. Yeah. So it's a solution that, I mean, it's an equation that has no manually closed form manually, so you will use your calculator to solve for beta. Once you solve for beta, then you can draw your waveform. Okay? And then after beta, of course, the value of current is zero because this is because of the circuit that we're using, the RL circuit. Any questions? The rest of the equations are identical, except for what? For example, when we have a DC source, we're starting, instead of zero, we're starting a little bit later at alpha, right? At where the DC source and the AC source equal to each other. But the shape of the current is always the same. Our objective is always to find what? We have to know the value of an equation for voltages and an equation for current. So if you want to calculate, power factor, if you want to calculate total harmonic distortion, if you want to calculate power into the load, power from the source, all of that requires what? Knowledge of the equations of voltage and current. Voltages are nice and easy because they're sine waves. So all we're going to be doing in this chapter is really finding the equations for currents. And they're going to be all very similar because of the fact that they just all have the same shape. They just start at different points. So this starting at different points is the shift of axis that we're going to do. Right? So you see the flow of what we were trying to do? It's simple. Don't complicate it, really. It's simple and the equations are not difficult. So again, stop me if you have questions on the waveforms. We went through all of them, but if you have questions about the waveforms still, you please feel free to stop me. So we finished the RL circuit now with the diode. And then the book goes through an exercise with PSpice that I think is nice. I mean, again, I recommended you to, I think the question that was asked by Khan last time about, beta, and is it going to change with when the current starts later. I'm not sure if you simulated that on PSpice. Did you simulate the question that you had last time on PSpice? The extinction angle? You asked the question in class.
I don't know.
You should go back and simulate. Yeah. So please try to do that. Please try to do that. I mean, the book has a good.
We were having some trouble with PSpice. It
Okay.
was Ian Moody.
Keep trying. Keep trying. So this example, for example, they ask you to find the value of R and L to produce a specific value of average current. So you know that you're producing a current that looks like a certain shape of the current. With PSpice, you can actually ask it to do the calculation of average value for you. So it does the calculation of average value for you, and then you can ask it to sweep parameter values. So I don't know if you tried that or not. Have you tried sweeping parameter values with PSpice? So for example, you have different values of L. Here they started with 0.1, I think, until where?
I think we did that sweeping thing.
Yeah. So you can do the parametric sweep, and you can sweep the values of R and L, for example, until you satisfy the value of average current that they're asking for. This is just an exercise, right? These are the results. Okay, so now RL with a source. We said that the only thing that changes here is the fact that the current will start delayed with respect to zero, right? So it doesn't start at zero anymore. It will start where? At the intersection of the DC voltage and the AC voltage, right? Only at this intersection will current start to build. Only after the AC voltage is greater than the DC source will current start to flow in the circuit. So we go through the same logic, same process, right? We do KVL around the loop. So the input voltage source is equal to the voltage drop across the resistance, the inductance, and the DC source. So V maximum sine omega t is equal to Ri of t plus L di by dt plus the DC source, right? Now I want to find what? Current. Current divided into a forced response and a natural response. The forced response here is a little different than before because I have two sources. I have an AC source and a DC source. So my forced response is going to be due to the AC source and the DC source. So they divided the circuit up for you to look at the forced response due to the AC source, which is this voltage divided by the impedance. And then for the DC source, it's the voltage divided by the resistance because inductances are short circuits to DC, right? In DC circuits, in steady state, again, L di by dt does not exist. The di by dt does not exist. There's no change in current with respect to time. So you know that there's no voltage across the inductor. If there's no voltage across the inductor, if the voltage across the inductor is zero, di by dt is zero, so the voltage across the inductor is zero. When something has a voltage of zero across it, that means it's a short circuit, right? So for DC circuits, inductors are short circuits. So you don't see it here. So the forced response is the voltage divided by the impedance due to the AC source, and then the voltage divided by the resistance. But they are in opposite directions, of course, so that's why they use the minus sign here. Okay, so this would be the forced response. Natural response is identical. AE to the minus t over tau, right? So I take this now and add it to the forced response and write my full equation for current like I did in the last circuit. So I have an equation with the value of A here. What do I know about my circuit? I know that at alpha, I know that the current is zero. So I know that I of alpha is equal to zero, exactly the same as before, but before this alpha was zero. Now this alpha has a value, so I need to find out what this value of alpha is. What is this value of alpha? To find this value of alpha, I know it happens at the intersection of the DC source and the AC source. So if I equate my DC source with my AC source at the angle alpha, I should be able to solve for alpha. And that's exactly what was done here. So we did that here and found alpha. After finding alpha, I can now do what? Right, I of alpha is equal to 0. Right, I know alpha. I will substitute with I of alpha instead of the omega t here. And then the only unknown will be A. And you will be able to solve for A like you did before, and you will have the equation in your equation sheet. I don't even have it on the slide. It's in the textbook and the equation sheet. But it's the same process like before. Right, so you just solve for A after finding alpha. Any questions? Questions? Yeah. Tau is L over R. It's a time constant of the RL circuit. So we only have RL circuits or RC circuits. If we have a circuit that has L and a C, we will not analyze it. It's too complicated. Second order differential equation. We will always assume one is there and the other is not there. So it's a simplification that makes a lot of sense, yeah, and it makes your life a lot easier because you always know the solution to the differential equation in this case, right? AE to the minus t over tau. Okay. L source and a load. The book goes, has a small section on that. It's unrealistic, and I mentioned that in the slides. Again, just a mathematical exercise again here. What they do is try to find the current in the circuit. We're just trying to find currents in the circuit. So if you try to find the current in the circuit here, again, you have two sources, an AC source and a DC source. KVL around the loop. The input source is equal to the voltage across the inductor plus the DC source, right? So in this case, I don't have a resistor anymore, right? So I only have the LDI by dt term. So I do not need to solve a first order differential equation anymore. I just have a equation that I can integrate. So if I solve for the current here, I can integrate and find the value of current, right? I do not have a first order differential equation. So again, it's unrealistic. They just try to find the value it's a mathematical exercise to find the value of current. Yeah. We didn't even draw the waveforms for this because even if you try to simulate it, it will not make sense. It will not converge. The simulation will not work. Yeah. Freewheeling diode. So what did the freewheeling diode do? Before the diode, what was happening to my output voltage beyond pi. Beyond pi with an RL circuit, remember, beyond pi with an RL circuit without a freewheeling diode. What was the output voltage? What did it look like? RL circuit, guys, come on. Beyond pi, what happened beyond pi? Exactly. That was, the output voltage was going negative for a while because current was continuous, right? So current was stopping here, so the output voltage was something that looked like my input all the way until here, right? But when I added the diode here, what does that do, right? Current is flowing here. It will not change directions because this is an inductance. I cannot change directions through the inductor. The current will not change direction through the inductor. Also, the current will only flow in this case, in this direction, because of the diode, right? So current will always remain like this in my load, right? And now I'm in the negative half cycle. So this is positive, this is negative. Before I put this diode, fine, I was forced, this voltage here, the opposing voltage here that what flipped in the negative direction, what it was doing was what? What it was doing was decreasing the current inside my inductance. It was decreasing the current through the inductor, right? So remember, when you have a voltage that's positive across an inductor versus when you have a voltage that's negative across an inductor, VL is equal to L di by dt, right? I is equal to 1 over L integral of VL dt, right? It's the current through an inductor is equal to the integration of the voltage across the inductor. So if the voltage is positive, what is the slope of the current? It's positive because if the voltage is positive, this value of integration is positive. So the value of integration is positive, then the current will always be growing, right? Growing at some form or shape, right? It will be growing. But if the value of voltage is negative, what's going to happen to the current? You're adding negative numbers. You keep adding, so this negative number will grow, right? So, and you have an initial condition, I of the previous case. So this is I of k, this is I of k minus 1. So you had, initially when you were when the v was positive, you had a I of k that was I of k minus 1 that was always a positive number. You added a small positive number to it, it grows, right? Now if the voltage is negative, I of k minus 1 was still positive, right? It was a positive number. Current was growing initially, and it's now a positive number. Now the v flip polarity, right? The integration is now a negative number. So I'm adding now a negative number to a previous positive number. So what's going to happen? The positive number will just reduce a little bit, right? So the current will be reduced, right? So the current will go down, right? It will decrease. The current will decrease in the circuit as soon as this happens. Right? As soon as the inductor has negative voltage across it. So it's actually a little bit earlier than that, right? We said that this is the output voltage. Inductor voltage was what? I think somewhere here it was equal to, so a little bit before. So whenever the slope was exactly 0, beyond that I had negative voltage across my inductor, the current started to go down, right? So this source was actually doing what? Helping this current go down. I mean, it was pushing this current down. If I remove the source and I just have the resistor, is the current going to go down? Yes, it will, but at a slower rate. Yeah, because the energy will be dissipated in the resistor, and fine, it will be there. But now I have a source that's also opposing the current, the voltage across the inductor, right? That's what this is doing here, right? So when I put the freewheeling diode, what happened? What happened to the output voltage when I put the freewheeling diode? This was the output voltage without the freewheeling diode. What happened to the output voltage when I put the freewheeling diode? Yeah, current was flowing this way, right? Now it has this path, which is a nice, easy path to flow through, or it has this tortuous path because it's a voltage that's pushing the current in the opposite direction. It's trying to do that, right? So which path will it flow through? The easiest path. Exactly. So it will flow through this path. So if current flow through this path, then what's the output voltage equal to? What does V out equal to? This is now the current's flowing through here. So what is the value of V out? This is a short circuit, right? When current's flowing through it, it's a short circuit. So if there's a short circuit here, what is the voltage on the output? Value. What's the value of the output? Zero. Yeah. I mean, the voltage across short circuit is zero. There's no voltage across. It's zero, right? So as soon as this diode turns on, the output voltage becomes zero. Before that, it was doing the same thing as the previous case with the RL load. Right? It was equal to the input voltage because this diode was on. As soon as this diode turned on, diode 2, then the output voltage became a zero. Right? But current was still flowing. Right? Current was still flowing all the way until here. Okay? Okay. Good question. A question now. Current was still flowing. That's fine. Until here. In this portion, diode 1 was on. Do you agree? And this portion, diode 2 was on. Do you agree? So what is the shape of source current? IS. When diode 2 is on, is there any current coming from my source? So that's good. So at least we know that in the, so this is my cycle. Diode 2 turns on right here. Current looks like this. So I know that when diode 2 is on, the source current is 0. And then when diode 1 is on, what is the source current? Same as diode 1 current, right? So the source current looks like this. 0. And starts again like this. 0. But load current is this. This whole shape is load current. How about diode 2 current? Diode 2 current would look like 0, and then jump here, and then this portion. Right? So if I asked you to calculate the average power loss in diode 1 versus the average power loss in diode 2, right? It's different. You would have to find the average value of this waveform versus the average value of this waveform. For example, how would you find the average value of this waveform? You have the equation for current, right? And we know that, and if you were able to calculate beta for that RL case, then you know this point, beta, and then you know this point because it's pi, and you integrate you integrate the equation for current over the period, right? The integrations you can do with the calculators, guys. I don't have a problem with that. Okay, but at least you need to write the equation that you will integrate, right? So everybody's okay with the waveforms? Some of these questions are not, like in the textbook, like the waveforms, maybe they're not drawn in the textbook explicitly. Draw the capacitor current, draw the source current, draw this diode current, draw that diode current. That's why when you go through P-Splice and, put current markers and voltage markers everywhere. and look at the voltage across the resistor, look at the voltage across the inductor, the current through this, current through that. Okay. So now we reviewed this circuit now, and then we will do the same thing we go through, and we want to find the equation for, because the voltage looks, it's the half-wave rectified sine wave, right? Because as soon as we put the freewheeling diode, it's very simple. The half-wave rectified sine wave, we know the equation for voltage, right? How about the equation for current? The equation for current in the load is exactly as before, right? Did the current change shape? The load current. The load current is exactly the same shape. It has a forced response and a natural response. Forced response due to the source, natural response due to the RL circuit. The equation will be identical. Only thing that changes is the shape of the voltage. It's a pure half-wave rectifier versus having this negative section like before. Okay, so that's why they drew these two circuits. And when diode 1 is on, I have my forced response, and then I have my natural response in here. Right? So, and the equation is exactly the same as before. That's why I didn't even write it down. It's exactly the same as the case with the RL circuit. Right? Nothing changes here, but voltage changes. The average value of voltage changes. The RMS value of voltage changes. Harmonic content. I mean, no, there's no harmonic content. The harmonic content doesn't change, sorry, because it's a pure sine wave anyway. How about if I keep increasing the value of L? So we drew the waveform here. Current was extinguishing at beta. If I keep increasing the value of L, what did we say will happen? Beta changes. So beta will change from here to here to here. How about what happens here? Here, all of this, the voltage across the inductor was negative. At some point, the source flips polarity. The voltage starts to become positive again, right? So if the voltage starts to become positive again, right, the VAC is equal to VR plus VL, right? So VL is equal to VAC minus VR, right? So at some point, this AC voltage will become positive, right? At some point, this AC voltage becomes positive again, like it was doing here. So if the AC voltage becomes positive again, and assuming I had a very large value of L, then I may have still current in my circuit, right? So there may be still a value for VR. And this VR value may still be positive. So it will not happen exactly at this point, maybe a little bit beyond. Maybe a little bit beyond this point when VR and VAC become equal. Okay, I cannot draw it exactly because it's a number, right? It's a fixed number. At some point, not necessarily at the zero crossing of the voltage source. At some point, the value of VL becomes positive. Do we agree? If I keep increasing inductance, the B will keep increasing. The B will keep increasing. So this value, the current shape will continue to go, it will fall later. At some point, and this current is flowing through my resistor, so it's affecting the value of VR, right? At some point here, my VAC becomes positive again. So VAC becomes positive, but there is a bigger value of VR because there's still more current flowing in the circuit. So maybe this point is not what I'm looking at. Maybe a little bit beyond where the voltage crosses zero, what will happen is VR will become equal to VAC. At an instant beyond that, VAC becomes higher than VR. If VAC becomes higher than VR, what's the polarity of voltage across VL? Positive. If I have positive voltage across VL, what's going to happen to the current? Increase again, right? So, it was decreasing, current was decreasing, and at some point, current will start increasing again, right? So then I have this current flowing that is, like a ripple of current flowing through my circuit. Okay, and this current never touches zero, right? It never goes down to zero because it's gonna always, beta is always gonna be the same because I have the same RL values, and then I will always start raising the value of current again beyond this 2 pi, beyond every period here. Okay, so if the current does not touch the zero value, it's called continuous conduction mode, right? So there's always current flowing in my circuit. Current is flowing in my circuit continuously, right? So that's continuous conduction mode. If current touches zero, then I have a discontinuous conduction mode. Okay? It's just terminology that we use. To be used more interesting later when we talk about switch mode power supply, like DC to DC converters. Yeah. Here it's okay. It's something to understand. Okay, so this is why this waveform is drawn. I didn't want to show this waveform without explaining it, right? So do you see why this waveform is the shape it is? It's for very large values of L. This is what happens to the current. It becomes continuous, the output current, right? Okay, so now we have that. So now it becomes a bit difficult. Okay, so why did we show this? Before it was nice and easy when the current was falling at beta here. I was able to find the equation for current, right? I wrote my forced response and natural response, and everything was nice. I was able to find my equation for current. I knew some initial conditions. Perfect. But now, when the current becomes continuous like this, it's very tough to find the equation for current. I do not know how to find the equation. I don't have an analytical technique that's simple like before to find the equation. I cannot solve a differential equation, for example, because differential equations with sines and cosines depend on the having sines and cosines that where quantities are crossing zero. Here, quantities are not crossing zero, right? So what's going to happen? What's another tool that I can use? I know the shape of what? My output voltage, right? If I know my shape of my output voltage and I know my load impedance, what can I do? I can use voltage divided by the impedance, right? So I can use the Fourier series to help me with that, because you have a Fourier series sheet that gives you the value of the Fourier series components for this output voltage, right? For this half-wave rectified output voltage, it's one of the waveforms that you have in the sheet, that the Fourier series sheet that you have. So if you have an equation for the voltage on the output, and you know your impedance, R and L values, then you can use the Fourier series to take each component of voltage and every frequency corresponding impedance and find the corresponding value of harmonic current. So you can sort of find the Fourier series of the current, or all the components of the current, the Fourier series expansion of the current, from the Fourier series expansion of the voltage and knowledge of your impedance. Everybody's okay with that? We had to do that because there's no way for me to find the equation for this current. I don't have a nice, easy, closed form solution to find current. And that's always our objective. We want to find equations for voltage, equations for current. If I have equations for voltage and equations for current, I can do everything else. I can calculate power factor, THD, I can calculate everything, distortion factor, crest factor, I can do everything, right? But I didn't have the equation for current, so we did it before in a certain fashion because we had a way to find a closed form solution. Now I don't have a closed form solution for the current, so the trick was to use the Fourier series for the voltage and the value of impedances to find the harmonic values of harmonic components of the current, or basically the Fourier series expansion of the current, right? It's the same. So I can just take, I rewrite, instead of V, I can just write I and divide here by Zn, right? Z0, Z1, Z2, Z3, so on and so forth. Everybody's okay with this? And then here they draw, they split the current into the diode 1 current versus diode 2 current that I explained as well. So diode 1 current is what's coming from my supply. Diode 2 current is due to the fact that I have energy stored in my inductor. Okay? If I make this inductance infinite, or L over R time constant infinite, then what happens? Then this current becomes a straight value, then the currents through diode 1 and diode 2 look more like square waves, right? And we have this passing of currents between diode 1 and diode 2 that we talked about before, right? And here they don't show the effect of commutation, of course. This is the ideal waveforms. Yeah. But we studied what commutation means, and we will look at the equations later in the chapter. Yeah. Any questions so far? We also looked at the capacitive output filter, and we went through the waveforms. Any questions on the waveforms? The current through the load. Okay, so let me. I think it's on the next slide here. So let me just do the equations, and then we'll go through the waveforms again. Okay. But actually, the current through the load is okay. Just to that. What will the current through the? You tell me. Why are you confused about the current through the load? It's a resistor, right?
Yes.
What is the voltage across the load? Same as the capacitor voltage. So what does the capacitor voltage look like? Remember, initially we were charging the capacitor, and then the capacitor was feeding my load. Right? So this is, now I'm charging the capacitor again, capacitor's feeding my load. Charging the capacitor again, capacitor's feeding my load. So this is the output voltage across the load. It will be a scaled down version of this. Okay? The tricky ones are the capacitor current and the source current. I have the source current in the next slide, and we did it in the last class, and I drew the capacitor and source current last class. We can go through that again, no problem. Okay? So let's just go through the equations first to make some sense of, how do you design C? In this case, how do you select C, right? So we said that this bucket of water analogy, right? If I make C too small and I'm drawing too much water, then the level is not maintained, right? And our objective is to do what? Maintain the level. The level is the voltage across my load, right? So if I'm maintaining the voltage across my load, I can have a nice smooth current, right? So our objective was always to do what? Control the ripple voltage, right? That was the whole objective of this exercise of adding this capacitor. That was the whole objective. So to do that, to control delta V, what is delta V equal to? Delta V is the difference between the peak value, right, and the minimum value, right? It's the peak value and the minimum value. Peak value, and that's the difference between them is delta V. So I would like to find an equation for that. So what is the peak value of voltage across the load? It's V maximum. That is the peak value of voltage across my load. It's V maximum, right? How about what's the minimum value? The minimum value occurs here, right? It's the intersection of two waveforms, correct? It's the intersection of the exponential and the sine wave. It's the intersection of the sine wave at 2 pi plus alpha, correct? At 2 pi plus alpha, this is where, I know that this is where this occurs. I call this alpha. So at 2 pi plus alpha, there is this intersection. At this intersection, I would like to find the value of both waveforms, the exponential and the sine wave, right? So if I equate the equation for this exponential and V maximum sine 2 pi plus alpha, right, I can find the value that I would like. I can find alpha. So let's see. So delta V, we'll start from the bottom up, okay? So delta V here, we said is the difference between my maximum voltage across the load, which is V maximum here, and V maximum sine alpha. So this is V maximum sine alpha occurs here, right? So this is the point where V maximum sine alpha occurs. So it's V maximum minus V maximum sine alpha is my ripple voltage. So we all agree this is the equation for ripple voltage? Okay, so this equation has alpha that we do not know about, correct? I mean, the only thing, we want to calculate delta V. Remember, the objective of adding the capacitor was to control delta V. So now I found an equation for my delta V. This is the equation that we can understand quickly right now, right? So this equation has an alpha that I don't understand how to calculate, right? So we have to figure out a way to calculate the alpha. So how do we calculate the alpha? We calculate the alpha by equating this exponential, and the sine wave at this point alpha. So the equation for the exponential, okay, so these are the equations for the sine wave, it's V maximum sine omega t. The equation for the exponential is ae to the minus t over tau, right? That's always the RC circuit time constant that we have. After we solve for a in this case, we will have a equal to, it's this v theta. A is, in this case, they call this a, they call it v theta. So it's v theta or a e to the minus t over tau. They shifted the axis here by theta because the exponential did not start at 0, right? It did not start at pi over 2. It started at a point theta. What did we say this point theta was? Exactly. Exactly. The point theta is where the slope of the sine wave versus the slope of the exponential were equal, right? So I have my sine wave equation and I have my exponential equation. If I differentiate my sine wave equation and I differentiate my exponential equation, that's the slope. And I equate the slopes. If I equate the slopes of these two equations, that's what they did here. So they differentiated this, V maximum cosine theta. They did the differentiation where? At theta, right? It's the differentiation at that point which happens to be theta. So the V maximum cosine theta, and then they differentiated this, and it was this big number at theta as well. So at theta, they replaced omega t with theta, and they were able to simplify that and solve for theta. Right? So now I solved for theta, so I know where theta occurs. But that doesn't still help me here because I need to know where alpha is. Right? So where does alpha occur? Alpha occurs at the intersection of these two waveforms. Not here. What we did was we wanted to find where theta was. Why did we want to find where theta was? Because of this equation. So initially we wanted to find alpha. How did we find alpha? We said that we find alpha by equating the exponential and my input sine wave at this point 2 pi plus alpha, right? So if I take my exponential waveform, which is this v theta happens to be v max sine theta at this point, okay, and write the exponential equation at 2 pi plus alpha. So instead of omega t, I write 2 pi plus alpha. So I end up with v max sine theta exponential minus 2 pi plus alpha minus theta because of the shift in axis in the exponential here, and then divide that by omega RC because I have an RC time constant. So I equated the exponential and my sine wave at the point 2 pi plus alpha. If I do that, I end up with an equation that has alpha as well as theta. Right? So initially I wanted my delta V. My delta V was a function of alpha. I needed alpha, right? So for me to find alpha, I found the intersection of the exponential waveform and the sine wave, which was this equation. It's the intersection of the exponential and the sine wave at 2 pi plus alpha. So I took my sine wave, replaced omega t by 2 pi plus alpha. I took my exponential, replaced omega t with 2 pi plus alpha. I equated them together. If you equate those together, you will find an equation that's a function of alpha, which is great. I would have solved for alpha and been finished, right? The problem is I ended up having an equation that also includes theta. So I need to find theta. So how did we find theta? We go to this point, because we used this point already. Now we go to this point, and we find the point where the two slopes are equal to each other. So the 2 points where the two slopes are equal to each other is the differentiation of the two voltage waveforms. So I took my two voltage waveforms, differentiated them, and equated them. This gave me a solution for theta. So now I have theta. I can plug it into this equation, which is, after simplification, it's this equation. So I can plug it into this equation. Now I have an equation that only has alpha unknown. Right? Initially, I was trying to solve this equation that had alpha and theta unknown. I found a way to find theta, so I plugged it here. I only now have an equation with alpha unknown. If you have an equation with alpha unknown and you use your calculator, because it's a numerical equation as well that cannot be solved, that does not have a closed form solution manually, so you will need to use your calculators to calculate alpha. If you calculate alpha, then you can plug everything into this equation and calculate the exact value of delta V. You can do that, right? That's the long way to do it, right? And it works. This will give you an exact solution, right? Or we know that if my circuit is properly designed, meaning what? Meaning my RC time constant is large enough, maybe a couple of times larger than my initial input frequency. If that's the case, we know that theta, which is this point at which the slopes split, is almost equal to pi over 2, right? We know that. We know that if I've properly chosen my capacitor value and according to my load, meaning I've properly sized my bucket according to how much water is coming out of it, so that I'm able to maintain the level sort of constant, sort of at the where I need it to be, then I know that the level of my bucket of water, the level is approximately, I don't know, 1 meter, for example. I know that it's approximately that. Fine, it goes up and down, but I know it's approximately that, right? And that's exactly what happens here. I know that if I've properly chosen my capacitor value according to my load, then theta should be approximately around the pi over 2 area. So then I've, this equation initially what? I had a problem finding alpha and theta, right? So now I've solved theta quickly without this mess, right? Theta is pi over 2, approximately, right? So I've simplified matters quite a bit here. And I know that V maximum approximately equals V maximum sine theta. So, I mean, V maximum, since theta is equal to pi over 2, right? So that's what this says here. So if you do this simplification, the book goes through some derivation and comes up with an equation that relates your voltage ripple with your capacitor and resistor value and frequency. So here, what did I do? Here I came up with an equation for voltage ripple in terms of what? In terms of my alphas and thetas and my R's and C's, right? So basically I came up with an equation for ripple in terms of my R and C, as well as the points where the waveforms start intersecting. So I sort of know time, I know times, I know my RC time constants as well, right? So the book goes through the same derivation. So it goes through a derivation where it simplifies the fact that theta is equal to pi over 2 and comes up with an equation for delta V that you can directly use, right? Assuming what? Assuming you have chosen R and C, the RC time constant to be larger, quite larger than your fundamental period, right? If it's not, then you cannot use the simplification, because in the homework it asks stuff like that. It tells you sometimes that, oh, my RC time constant is very low versus my RC time constant is very high. Which equation do you use? You cannot use this equation if the RC time constant is low, if it's equal to the period. You cannot do that, right? Because then this is an approximate solution that is telling you that the voltages are, this maximum voltage is always up here. This theta is always happening up there. Theta happening up there means the load is very low. Remember, when theta goes further away from this peak, why is it doing that? When these two waveforms are splitting further down, why is that happening? Let me draw the waveforms again. This was your input voltage. And then I was charging my capacitor. We agree? This is my diode capacitor resistor circuit. Right? So I was charging my capacitor from the source until here. Right? And then what happened? We said if there is no resistor at all, if I'm not consuming, so initially I was charging my capacitor from my source. So the capacitor voltage started to build up, it equals the source voltage. If there is no resistor at all, no current is going to be drawn out of this circuit. No current will flow here, right? So if no current is flowing here, and this capacitor voltage is at this point here, is the capacitor voltage going to ever go down? It won't, because if the capacitor, what's happening now is that the source voltage will start going down. My input source voltage will start going down. If my input source voltage starts going down, and my capacitor voltage is maintained because I'm not drawing any current out of that capacitor, then what happens to this diode is that it blocks. Right? So if this diode starts blocking, then I have a circuit that looks exactly like this. Just the capacitor. Capacitor feeding nothing. Right? Its voltage will never change for an ideal capacitor. Will this voltage ever change? Assuming there's no leakage, the circuit is not closed, nothing, right? It's an ideal capacitor. It will maintain the voltage. You've put voltage across it. You've charged the capacitor plates, so you've created voltage. The voltage will go nowhere. It will remain across the capacitor terminals, right? It will do this. But if I now connect a resistor here, what's going to happen to my capacitor voltage? It will decrease, right? It's if you have now your, the 214. You have a capacitor, an ideal capacitor, and then you put a voltage source. Remember when you were doing that? And the voltage source has an initial value of, has a value equal to the what? Has a value equal to the initial capacitor voltage, right? So you have now a circuit with a source, a capacitor, and a resistor, and you do the solution. The solution is AE to the minus T over tau, right? It's a first order differential equation where tau in this case is equal to RC, not L over R, right? And the capacitor voltage will decrease. It will decrease exponentially. Is it going to decrease this way? Or is it going to decrease this way? Or is it going to decrease this way? Depends on what? Depends on the value of R. If R is very small, so it's drawing a lot of current, the capacitor voltage will fall very quickly. If R is very large, almost equal to infinity, almost equal to an open circuit, then capacitor voltage will not fall at all, theoretically speaking. There's nothing such as that, but theoretically speaking, it will be maintained all the way up there. Right? So this point, initially the point theta was up here. Theta was equal to pi over 2 initially. Theta is where the source voltage and capacitor voltage slopes start differing. If the capacitor voltage stays equal to maximum value, right, theta is equal to pi over 2. Because right beyond pi over 2, source voltage starts to go down. Its slope is going to change versus the capacitor voltage slope. Capacitor voltage slope will still be 0, right? But if I'm drawing a little bit of current, then the theta moves a little bit, right? Theta moves a little bit. This green waveform, will part away from that red waveform a little bit beyond pi over 2. For if I'm drawing a little bit of current, if I draw more current, this theta will move a little bit further, and theta moves a little bit further with this red waveform, right? So this theta value depends on how much current you're drawing out. Okay, so that's why the approximation that they're using here, this equation is an approximation. The approximation relies on theta being almost equal to pi over 2. So if theta is almost equal to pi over 2, meaning your RC time constant is quite large, 3-4 times your fundamental cycle, that means your voltage across the capacitor will not fall quickly. In that case, they were able to come up with a simplification using some derivation in the textbook that I don't have on the slides here. I don't care for you to memorize the derivation because we already understand this. The important thing is to understand the initial equation. Okay, this is the exact solution. The exact solution, we understand where it came from. We had delta V, V maximum minus V maximum sine alpha. We understand where that came from. And then, fine, we found alpha and theta, etc., etc. Okay? So any questions on the equations here? So as you see here, if the capacitance value is very large, delta V is what? Small. Makes sense. If my bucket is very, very large, the level of water in the bucket will be small. If my resistor becomes really, really small, so I'm consuming a lot of drawing a lot of water out of the bucket, or I'm drawing a lot of current out of the capacitor, then if this is very small, if R is very small, then delta V is very large, right? And then F is a little bit of a funny thing, right? So how does F come into play? Think of the bucket thing. Think of the bucket analogy as well, yeah. So if you have a bucket and you are drawing water out of that bucket at a frequency that's very low. So let's say you have a small bucket and you draw a certain volume of water out of that bucket. So the volume of water that you're drawing is what's needed for your load, for your garden, for example, right? What's going to happen to the level of the water? So you're going to draw a certain volume, the level will go down, right? But what if I do this at a much faster rate? My load, which is my garden in this case, needs the same amount of water in the same amount of time, right? So now I take, instead of taking this volume one time, because I'm taking it at a very low frequency, every day I'm watering one time. So the level will go down, and then I refill it up. That's my frequency is 1 day, right? Now I'm able to control frequency to be 1/100th of a day. So, but my garden requires the same amount of water, right? Or otherwise the plants will die, right? So then I take a small amount of water, and then replenish. Small amount of water, replenish. Small amount of water, replenish. Small amount of water, replenish. What's going to happen to the level? It's almost fixed, right? For the same bucket, right? So for the same bucket and for the same garden, which is my load, right? In this case, if I increase the frequency of my job, my work, then I can live with a small bucket, right? So that's what this equation tells you is if you increase the frequency of doing this, of this action that you're doing, this delta V occurring, then you should be able to live with a smaller bucket, meaning a smaller capacitor, right? We will do more of that later down the road, yeah. Any questions on this? The equations, okay? Everybody's okay with the equations? Sorry, the last set of equations. I know waveforms are important, but more equations. So I really want to finish this chapter, the equations for this chapter. And it's the equation for when we add the SCR, what did we do to our basic half-wave rectifier? We delayed the output voltage going, or the output current flowing to the load, right? So now the value of average voltage is 1 over the period integration of the output voltage over the period. But now I don't start from 0, I start from alpha. So what does that mean? That means that my output voltage will have a controllable element here. And this controllable element is due to the fact that I can delay the start of conduction of my diode, or my SCR in this case. So now I can decrease my voltage all the way down to 0, because this cosine alpha ranges from what? -1 to 1. Right? If it's -1, then my output voltage is 0. If it's 1, my output voltage is 2 V maximum over 2 pi, or V maximum over pi, which is equal to the half-wave rectified equation. Can I make it negative? Can I make it negative? I cannot make this negative, okay? So that's fine. And then they calculated the RMS value as well. But how about if I add an inductor? If I add an inductor, we said that this will cause current to continue to flow. If current continues to flow, then my output voltage will go negative. They didn't draw the output voltage here. But the output voltage will continue to flow. And the current will start flowing from the point of conduction, which is my alpha, and will stop where? At beta. If I choose alpha and beta here in a certain fashion, can I make the output voltage have a negative value? This has what? So this is the output voltage equation. This is the output voltage equation, right? It's V maximum over 2 pi cosine alpha minus cosine beta, right? So this is between minus 1 and 1. This is between minus 1 and 1. So if I make this 1, cosine beta is equal to 1, and cosine alpha equal to minus 1, I can, theoretically speaking, if the inductance, actually in this case it requires the inductance to be very, very large, then I can theoretically speaking make the output voltage look negative. But the catch is here, it has to start when it's positive. I mean, you cannot make, there's a limit, there will be a limit on alpha. I mean, you cannot make alpha beyond pi over 2, because if beyond pi, if alpha is beyond pi, what's cosine alpha? What's cosine 180?
Cosine 181.
It's what?
1.
Cosine 180 is 1 or negative 1?
Negative.
Negative 1. So there will be a negative 1 would be here. So if cosine 180 is negative 1, then this will be a negative number, and then in this case this will be also a negative number, right? Because beta occurs after 180 as well, right? So you'll have two negative numbers, but this will become a positive, right? So it's negative of a negative will become a positive. So I think you can make the voltage be 0. I don't think you can make it flow negative. It's supply current, the DC. What happens if I want to use transformer? Yeah, so it's if you try to flip the polarity here, what's going to happen? You try to make this go negative, the average value go negative. You're going to try to flip current in the opposite direction, and the SCR will stop conducting it. Right? So you cannot flip the direction of current, but you can make voltage negative, have a negative value for. How about if it's will it have an average negative value? I don't know. We need to calculate the average value of current. Yeah, but I don't think. According to this, I don't think so, because beta will be beyond alpha. Alpha, if alpha is pi over 2, then you cannot do that. Yeah. But you can do that with the full wave rectifier, which we'll study next. Okay, so this equation has some more controllability, right? Right, it's a little bit more interesting than before. But what does the shape of the current look like? At the end of the day, remember we were trying to find the equation for current, right? The current shape is exactly the same shape as the case for the R circuit without a diode, without an SCR, right? It's still, at some point alpha, instead of at 0, current will rise. At some point beta, it will extinguish, and it will depend on the RL time constant. So the equation for current we'll find is exactly the same as before. Forced response, natural response. Forced response is equal to the voltage over the impedance. Natural response, AE to the minus T over tau. How do you find A? You find A from the fact that I of alpha is equal to 0. Then you substitute and find A. So they found A for you, and they put it here, and that's what you have in your equation sheet. Beta, I of beta will equal to 0 as well. But that is not a closed form, so you cannot find a manual hand closed form solution, so you have to do it numerically with your calculator. Exactly the same as before. Okay? With the source, does the shape of current change? Does not change. So this is exactly the same as this case, except that I have to, the DC the firing angle will have to be after the AC source is greater than the AC source, the DC source. If the AC source is greater than the DC source, the circuit can conduct. The circuit can conduct, and then I provide a firing angle. As soon as you provide a firing angle, what happens? The current will look exactly the same. Start at a certain point, extinguish at a certain point, right? And the shape will exactly be the same. So the equation for current will be exactly the same, except that the natural response of the circuit will be the same. The forced response will still have the DC, the minus VDC over R that we had in the previous case with the diode, without an SCR. Right? So it's exactly the same as the equations for the diode case, but I have an alpha in the picture. And commutation. We said what the effect of commutation is losing some part of the output voltage. We described the waveforms. So I know this is the shape of my output voltage waveform. This is the half-wave rectified waveform. If I don't have any commutation effects. If I have a commutation effect, I would like to know how much voltage I lost, right? We said that because the two diodes are on, then the output voltage is equal to 0. That was the explanation last class. So we lost a piece of the output voltage. This piece was until value U. How do you find this value U? It's the point where the diode current becomes 0. So I need to find my diode current. How do I find my diode current? Both of these devices are on. If both devices are on, what is the circuit current here? It's this voltage source across the inductor. VL equals M V max sine omega t. So this is the voltage across the inductor. How do you find the current? You integrate the voltage across the inductor. So they did the integration, which is V max over omega Ls, 1 minus cosine omega t. This is the voltage, this is the current flowing through the circuit on this side from the source. And then this is, assuming I have a fixed output current, then I can find ID2. ID2 is what? The difference between the load current and the source current. Source current I found from the voltage across the inductor. I integrated the voltage across the inductor right here. This is this term, right? And then the output current is a fixed DC value. It's an assumption. I assumed it's a fixed DC value here. Fixed, right? So if it's fixed, then I subtract it from each other. Then I can find ID2. ID2 at angle U will equal 0. So I substituted with IDU of equal to 0 in the equation for ID2 current, and I found U. Right? So you found U. If you found U, then you can find the effect of commutation on the output voltage. Right? So we went through all the equations now in the text in the chapter. Yeah. So I think if you understand the waveforms, the equations will be very simple, guys. Okay? So try to go through them, please. The nice thing is the next chapter, for the full wave rectifier, the equations are identical. So we will go through all of this again. So don't feel left out or don't feel confused. I mean, you'll find that the equations in the next chapter will be identical. The waveforms will be a little different because we have a full wave rectifier circuit. But the logic is very, very similar. So please review this. I wanted to do a